In this short video, we'll look at an application of Kirchoff's voltage law to the basic RC circuit. So here we have an RC circuit consists of a resistance R, capacitance C. We're taking the output voltage across the capacitor, and VI is the input voltage. So the first thing you do is apply the direction of current. Clockwise is positive. And this is a loop here. We sum all the potentials across the loop. Now keep in mind that if this current direction as it goes forward hits the negative of a power source, Vi is a power source, then that voltage is considered negative. So in this case Vi will be negative. So we'll apply Kirchoff's current voltage law. VR plus Vc minus Vi equal to 0. VR is the potential drop across the resistor, Vc is the potential drop across the capacitor, and Vi is the input voltage. And you know why this is negative, because when you march along like that, you hit the negative sign first. Now this is a temporary configuration of this voltage. In this particular at this particular configuration, this happens to be plus or minus, and this is minus. Vi is in fact an AC signal. So we'll substitute values. For if current I flows through resistor R, then the potential drop VR is I times R. Now Vc is nothing but Vo. We'll keep it as is. So we are interested in the input-output relationship. So we need to eliminate everything that is extraneous. So when I say input-output, we have Vo is the output, Vi is the input. We have to eliminate I from this equation somehow. We know that V0 is Vc. I already said that. The charge in the capacitor is given by capacitance times voltage drop across the capacitor, which is V0. And if I take this and differentiate with respect to time, I get current through the capacitor, and current through the capacitor is C times the rate of change of voltage across the capacitor, which is dV0 by dt. Capacitance is constant with respect to time, therefore you don't apply the chain rule here. Now what we do is we can substitute for I as this term, and V0 is nothing but equal to Vc. And you put everything together like so, and I get my differential equation. Now if I want to find the transfer function going from Vi to V0, and apply the Laplace transform with zero initial conditions like so. So Laplace of dV0 by dt is s times V0 of s, and others follow, and I can get an input-output relationship in the Laplace domain. This is the transfer function of this circuit. In the next example, we'll look at an RLC circuit, and in this RLC circuit, we are taking the output as the potential drop across the resistor. Same thing, we'll apply the current direction in this loop, the clockwise direction. Current in the loop is I. In this configuration, I've selected V to have positive here, negative here. When I do the summation of all potentials, this V will become negative because current is going to hit the negative first. So apply Kirchoff's law. VR is the potential drop across the resistor, VL is the potential drop across the inductor, VC is the potential drop across the capacitor, V is the input voltage, and VR, potential drop across the resistor, is the output voltage, which is I times R, and I can write I equal to V0 divided by R. You know that the potential drop across the inductor is L times di by dt. Potential drop across the capacitor is given by Q by C, where Q is the charge in the capacitor. Q is nothing but integral of the current through the capacitor with respect to time. So that's how I got that, and this follows here, and that is my differential equation. Now I can do the same thing, apply Laplace transform with initial zero conditions, or zero initial conditions I should say. Now we know Laplace transform of V0 of t is V0 of s, d V0 dt the Laplace transform of that is s times v0 of s, and Laplace transform of integral of v0 with respect to t is v0 of s divided by s. Laplace transform of v of t is v of s. And we can write the relationship v0 by v as this, simple simplification, and this is your transfer function. That's the end of this lecture.